Assalamualaikum, selamat sejahtera to all students. So in this video I will explain on the multiple stage of NLE, okay, chemical extraction or the partially immiscible system. Okay, so I just want to highlight again on the immiscible system. So immiscible system means immiscible itself, the word means the solvent or the liquid do not mix, okay, with each other, cannot be mixed. The two liquid cannot be mixed, and if it is partially immiscible, means the half of the system, the solvent can partially mix with the feed, okay, and partially immiscible with the feed. Okay, so I will start with the flow diagram first. Okay, so this is the flow diagram for the multiple stage. Okay, if you can see, there is stage 1, 2, and I will denote as n. Okay, and it will goes on. Okay, 1, 2, 3, and it will goes on. Okay, so let me draw for you. So this is stage 1. Let's say I have stage 1, 2, and I will put 3, and I will put n here. Okay, so the flow diagram, it will start with L node. So this is the feed. So usually in LLE we have a component A and B. Okay, component A and B, we want to separate A from B. So it will enter the system as feed. Okay, we put it as L node. So L node means it is a fresh feed. So the fresh feed we put as L node. So the L node and we have a solvent here. Okay, the solvent stream, we put it as Bn plus 1. Okay, n plus 1 means it is a fresh stream. Okay, solvent. So usually solvent, if it is a pure solvent, so it only contains component C. Okay, so A and B is 0. So for when the solvent and the feed mix, okay, in the system, it will produce a product. We call it as, here is extract. I will put as V1. Okay, the V1 means stream that comes from the tray or the stage 1. Okay, so this is the extract, and usually extract, because of this is partially immiscible, so it will have a 3 component. Okay, so the same thing will goes here. So it will the residual of, we want to extract A, okay, by using solvent. So the residual B, it will exit the system as a raffinate stream. We put as Ln. Okay, so Ln, and it will contain component A, B, and C. Okay, so this is the flow diagram for the multiple stage partially immiscible system. Okay, so immiscible means it cannot mix. If it is partially immiscible, means the half of the solvent, it can mix with the feed. Okay, let's say I have a, okay, let's say I mix the solvent with the feed. Okay, with the feed. For feed, I have a component A and B. For solvent, I use pure solvent, so it has a component C. So I mix it because I want to separate A. So C will extract the component A. So what will happen here, it will form an intermediate phase. We call it as M. Okay, intermediate phase. So it will mix here the solvent and the feed. So the intermediate phase then will be separated. It will form 2 types of product, extract and raffinate. So the M here, it will contain the component A, B, and C. Because of we mix the solvent which contain component C, mix with the feed which has the component A and B. So it will mix, and the intermediate phase mixture here, it will has all the component A, B and C. And after that, because of the system is partially immiscible, means the solvent, it can mix with the feed. So the extract and the raffinate, it will contain all the three composition, or all the three components. Okay, A, B and C, and raffinate also has a component A, B and C. Okay, so this system we call it as a partially immiscible system. Okay, when we after we draw the flow diagram, so next we want to know the material balance. Okay, the material, how to draw or how to construct the material balance from the flow diagram. Okay, so let's see. Okay, material balance. So as usual, we will have overall. We will have a component A and C. Okay, let's see. Overall is in is equal to out. Okay, this is the basic things on the material balance. In is equal to out. So the overall mass balance, it will become L naught. Okay, plus with the Bn plus 1, because of this is entering stream, L naught and Bn plus 1. So it will form an intermediate phase. Okay, so we will put M here. So the outstream is V1 and Ln. Okay, so if we want component A, the material balance in terms of component A, we multiply the stream or the flow rate with the composition. Okay, so let's say L naught. So the L naught we times with the XA naught plus Vn plus 1, we times with YEn plus 1, M with the component XEm. So V1 with the YA1 and Ln with the XEn. Okay, so for component C, we change the A with C now. Okay, L naught and XC naught plus with Vn plus 1 YCn plus 1 equal to M XCm and V1 YC1 plus Ln XCn. Okay, so this is the material balance that we need to solve the question later. Okay, so in multi-stage LLE, in partially immiscible system, of course we want to know, when we talk about multi-stage, we want to know what is the number of the stage required. Okay, let's say I have a component A and B. Okay, it enter as let's say component A got 0.4 mass fraction. Okay, B 0.6. I want to get rid of A from B. Okay, I want to remove A. Okay, my target is A is I want to extract as much as A. So the A that will left the stream, the system will only left with 0.1, let's say. Okay, so what if I have a target A, I want to achieve at raffinate, I want to get 0.1 mole percent. Okay, so what is the stages that are required by the system? Okay, so that is the main question, or that is the main objective in this multi-stage. We want to know how many stages are required to achieve our targeted component at the product. Okay, so for that we will use a graphical method. Later on I will show you on the graphical method. Okay, so if you can see the question, okay, So the schematic diagram of the system, okay, is same like I draw just now. Okay, so this is the schematic diagram or the flow diagram. You can draw the same thing like I draw just now. Okay, for question number 2, construct the ternary phase diagram, equilibrium diagram. So you should be able to draw the equilibrium diagram. I think I have covered this during topic single stage. Okay, so you should able to construct the ternary phase diagram. Okay, in the question the equilibrium data will be provided. Okay, so number 3, the composition of the extract and raffinate. So this is the same like single stage. You also need to calculate or find the composition of extract and raffinate. So this is using the graphical, the same solution or the same solution like single stage. And number 4 is you have to find the amount of extract and raffinate. So this is you will use the mass balance. Okay, so 1, 2, 3, 4. This is all same like the single stage solution. Okay, so for number 5, percentage of acetic acid being removed from the system. So the acetic acid percent remove, you can use the formula. So this is also same like the single stage. Okay, we already done this during the single stage topic. So the additional question is for multi-stage. We want to know the number of the theoretical stage. Okay, so 1, 2, 3, 4 and 5 we have covered in the single stage. You can use the same method or the same approach to solve this question. Okay, the only things that we need to solve additional question is we want to know how many stages are required for the system. Okay, so this is what I will teach you today. Okay, so let's draw the flow diagram first. When you got the question, you should be able to draw the flow diagram first. So I already draw the flow diagram. So you can fill in the information regarding the question. So let's read the question. Exercise 4.2, an aqueous feed of 200 kg per hour containing 40 weight % of acetic acid. You want to extract by using isopropyl ether. It's a pure isopropyl ether at the rate of 600 kg per hour in a counter current multi-stage system. So the acid acid concentration is to contain 10% of acetic acid. So equilibrium data is provided in the appendix. Okay, so let's fill in the information. So the feed contain 200. Okay, the flow rate is 200 kg per hour, and it contains 40 weight % of acetic acid. So the component A is 0.4. So of course the component B is 0.6. So at the feed we don't have component C. C is the solvent. Okay, so we don't have solvent in the feed. So we extract by using the pure isopropyl ether at the rate of 600. So the flow rate here is 600 kg per hour. When the solvent is pure means A is 0, B is 0, C is 1. So pure means it only has a one component. We call it as component C. Okay, so the acid concentration is to contain 10 weight % of acetic acid. Means at the raffinate, the composition of the acetic acid is 0.1. So B we don't know, C we don't know, and this one also we do not know. Okay, so this is what we want to calculate later. Okay, so schematic diagram I already draw. Okay, construct ternary phase diagram later. This one we have covered during the single stage topic. And next we want to calculate the composition of the extract and raffinate. So this is when we talk about composition, we must use the graphical method. Okay, so let's see. First, if you want to calculate, okay, we want to calculate the composition of the extract and raffinates, means we want to know what is the composition here, how many A and how many B and how many C in raffinate, and how many A and how many B and C in extract. So we want to know this. So first we will solve it using the graphical method, and before that we should find the coordinate of M. Okay, so why we have to find M? As I mentioned before, okay, so when we mix the solvent and the feed, it will momentarily form a mixture. We call it as intermediate mixture of M, before the M can be separated into the extract and raffinate. So we have to find M because of we know the solvent composition and we know the composition of the feed. So when we mix these two together and we form a mixture here, so it is actually an intermediate phase before we get extract and raffinate. So this is a very important point. So we have to find M in order to get the extract and raffinate. So how to find M? You should use the material balance. Okay, so for M, the overall, we start with overall balance, material balance first. So so L naught plus with Vn plus 1 is equal to M. Okay, so L naught is 200 plus Vn plus 1 is 600. It will become an M, which is 800. Okay, so this is overall. Okay, let's look into the component A. Okay, so the component A, so L naught XA naught plus Vn plus 1 YAN plus 1 is equal to M XAM. So L naught is 200. L naught is 200. XA naught, A is 0.4 plus Vn plus 1 is 600. YA is 0 and is equal to M. We already find M is 800 and we want to know XA. And so can we calculate XAM? So yes, we can calculate for XAM. So you will get XAM as 0.1. Okay, 0.1. Okay, let's find another coordinate for M. Okay, because M, it contains all the three components A, B and C. So next, let's find the component C. So in terms of component C, so you will change A to C. Okay, L naught XA XC naught plus Bn plus 1 YCN plus 1 equal to M XCM. Okay, so L naught is 200. So component C in the feed is 0. You put 0. Vn plus 1 is 600. So component C at the solvent is 1 is equal to M is 800 and XCM is the one that you want to calculate. So you can calculate for XCM and you will get XCM as 0.75. So you already find the coordinate of M. A is 0.1, B you don't know, and C is 0.75. So actually M is, to calculate the composition of P, you can simply minus 1 minus with 0.1 minus with 0.75 and you will get the composition of B as 0.15. Okay, so you already find the coordinate for M. Okay, So you refer or you go to the diagram. Okay, first you locate the coordinate for L, which is the fit. Number 2, you locate the solvent Bn plus 1. Okay, the solvent. And next you locate the position of M. Okay, so L naught, this is a right triangular diagram, so we only considering component A and C, which is A at the x-axis here. Okay, so Y is at the y-axis. S is component C at the y-axis. So L naught Vn plus 1, we only take the coordinate for A and C. So L naught A is 0.4, C is 0. So you put 0.4 and 0. Okay, component A and C. For Vn plus 1 is Vn plus 1, A is 0, C is 1. So 0 and 1. So for M, A is 0.1 and C is 0.75. 0.1, 0.75. So you already have the coordinate. Now you locate all the 3 coordinates. So L naught is 0.4. 0.40 is here, and 0.0 and 1 is here. Okay, so you join these two. You join these two lines, and next you locate M. So M must lie on Fs line. Okay, fit and solvent line. So M is 0.1, 0.75 here. So this is M. Okay, so next, okay, you already know the component or the composition of A and the raffinate. So raffinate, it contains component A as a 0.1. So you put 0.1 here. Number 4 is locate Ln. So Ln, it has a component A as 0.1, but you don't know the component C, isn't it? So you put 0.1 on the equilibrium line. Okay, so you join this is Ln on equilibrium line. So you join Ln with the M. Okay, so when you join the L with the M and you extend until you reach the equilibrium here, equilibrium line here. So this will be your extract component. Okay, so you read the coordinate, so this is your extract. Okay, so you will get 0.1 and 0.87. okay, so this is 0.1, the coordinate is 0.1 and 0.87. okay, so you will get V1 or the extract as a 0.1, 0.87. okay, so for Ln, just now you don't know the component of C, isn't it? So the Ln here the component A is 0.1, so you read the component C here, so you will get around 0. So you will get the component C around 0.02. Okay, when you read at the graph. Okay, here is 0.02. So here is 0.02. Okay, so now you have an extract and raffinate. Raffinate and extract. You have a component A and C. Now the full answer will be, so the ln or the raffinate 0.1, B 0.02, C. Okay, so B1 is 0.1, you don't know B, and 0.87. Okay, you can find the component B by, again, you subtract 1 with the minus 0.1 minus 0.02, you will get 0.88 here. And B1 you minus 1 with 0.1 and 0.87, you will get here 0.03. So this is the answer for the composition of raffinate and extract. Okay. Next, you need to calculate the amount of extract and raffinate. When we talk about amounts, it referring to the flow rate. Okay, flow rate of extract and raffinate in kilogram per hour. Okay, so this is the composition. We want to know the flow rate. Okay, so this is simply you can use the material balance. Okay, so use the same material balance, L node, XA node. Okay, plus with the Vn plus 1, Yan plus 1, M, XAM. Okay, so is equal to with V1, Ya1, plus Ln with the XAN. So this is for component A. Okay, and the component, we solve for component A first. Also, we want to know this one, L1 and Ln, V1 and Ln. So we take this part. Okay. So M we know is 800, XAM is 0.1. Okay, so this is from the previous answer. B1 is, we want to calculate B1. Ya1 is already find. Ya1 is 0.1 plus with Ln, the one that you don't know, XAN is actually 0.1. Okay, so 8 is equal to 0.1 V1 plus Ln 0.1 Ln. So this is one equation for component C. So for component C, you replace A with the C, L node, XC node plus Vn plus 1. Sorry. Okay, Vn plus 1, YCn plus 1. To M, XC, M is also equal to V1, YC1 plus with the Ln, XC, N. Okay, so V1 and Ln, so we take this part. So M is 800, so the C is 1. Okay, is equal to V1 is the one you want to calculate. YC1 is 0.87 from the previous answer. 0.87, and you plus with Ln, the one that you want to know. Okay, XCN is 0.02 from the previous answer. Okay, so you will get 800, 0.87 V1 plus 0.02 Ln. Okay, you solve. You have two equation and you have two unknown. You can solve. Then you will get V1 Ln as here. V1 687. Okay, 687 kilogram per hour, and ln you will get 112.94 kilogram per hour. Okay, you can solve by yourself this one. Okay, so let's see, the next question is you want to calculate the percentage of acetic acid being removed from the system. So this one you can calculate by using the percentage of acetic acid. Okay, so equal to L naught, extract, so means V1 you times with the YA1, you divide by the L naught, XA naught times with the 100. Okay, V1 is 687.06. You times with YA1 is 0.1, if I'm not mistaken, 0.1. Okay, 0.1. You divide by the L naught is 200 with 0.1. So you will get 85